Hi, I'm Chris and I'm back. In this video, I'll be writing a test procedure for the 16-bit floating point multiply operation. The source code for this video can be downloaded from GitHub. In the comments section, I've included directions for making your own local copy of the repository. The source code includes both the Verilog code for the 16-bit multiply operator and the test bench code for verifying the multiply operator. The test code for the original version of the HP class module tested all 65,536 possible 16-bit floating point values. How many test cases would I need to implement if I was going to test all possible inputs for the multiply operation? There are two 16-bit input values. Each of the input values can take any of 2 to the 16th power, or 65,536 different values. So for all combinations of input values, we would have to test 2 to the 32nd power different cases. This is over 4 billion different tests. This number of test cases is too large to handle with such a brute force technique, and this is only for 16-bit floating point numbers. To exhaustively test all the possible values for two 32-bit operands requires 2 to the 64th test cases. And for the 64-bit and 128-bit floating point formats, the number of test cases swells to 2 to the 128th power and 2 to the 256th power respectively. I'm going to assert that for the special cases, that is nans, infinities, and zeros, that a few representative cases will be enough. The breakdown of these test cases will proceed in a manner parallel to the way I implemented the multiply code for dealing with these special cases. I'll be reusing the table of input combinations which I filled out when implementing the multiply operation. I'll start with the first row of this table. I'm only going to write 6 test cases for this row. For each of the test cases, the multiplicand is going to be a signaling nan. The multiplier will be selected from all 6 IEEE value types, signaling nans, quiet nans, infinities, etc. Is this a valid way of testing the items in the first row of the table? I think so. If you remember, the Verilog code for this test case treats the value of the multiplier as being superfluous. If the multiplicand, that is the first operand, is a signaling nan, the Verilog code simply returns the first operand. The actual value of the second operand, or even the type of the second operand, has no impact on the value returned by the multiply module. I'm going to encode data into the significand of the multiplicand to make it easier to verify that the code did what I expected. I'm going to encode a hexadecimal A in the least significant 4 bits of the significand. For the multiplier, which is also a nan, whether it's a signaling nan or a quiet nan, I'm going to encode a hexadecimal B in the significand. I'm also going to encode a hexadecimal B into the significands for the subnormal and normal multipliers. I can't use this trick for the multipliers which are infinity or 0 because their significand values must be 0. If we run these 6 test cases, the result we should get for all 6 is hexadecimal 7C0A. In fact, that is what we get when we run these test cases. Let's decode these results. The letter P represents the product of the 2 input values. In parentheses, there are 2 values. The first is the hexadecimal representation of the product. The second value is a bit vector, where each digit represents one of the type flags returned from HP class. The first digit represents the SNAN flag. As you can see, the SNAN flag is set, which is what we expect when we multiply a signaling nan with any value. The remaining bits of the bit vector, in order, are the flags for quiet nans, infinities, zeros, subnormal numbers, and normal numbers. Please keep this information in mind as we move through the rest of the tests. For the last 5 rows of column 1, where the multiplier, that is the second operand, is a signaling nan, we can write a similar set of test cases. Remember that we've already tested the case where both the multiplicand and the multiplier are signaling nans, so there's no need to test it again here. For these 5 test cases, we should always get the return value hexadecimal 7C0B, and we do. Since we're done with all the signaling NAND cases, we only have 9 test cases left to finish testing quiet NANDs. To test the rest of the second row of our table, we can use the following code. For each of these cases, the value returned should be hexadecimal 7E0A, and they are. These are the test cases to finish the rest of column 2. By now you've probably guessed that each of these tests returns the value hexadecimal 7E0B. Testing the infinity case is a little more complicated because the value of the multiplier does have an impact on the product value which is generated. Looking at the table, we can see that there are 7 boxes left to be tested, which involve a multiplicand or multiplier, which is infinity. Infinities, zeros, subnormal numbers, and normal numbers can all be positive or negative. To exhaustively test these 7 boxes in the table, we really need to have at least 28 different cases. That is, positive infinity times positive infinity times negative infinity times positive infinity, negative infinity times negative infinity, and so on for all the different pairs of operand types. I'll start with the cases where the multiplicand is infinite and the multiplier is non-zero. Here are the corresponding test cases for the non-zero multiplicands in column 3. These 5 cases should all return positive infinity. I could make 3 more copies of these 5 test cases and manually modify the sign bits to generate test code for the positive times negative, and negative times positive, and negative times negative cases, but experience tells me that this is just begging to introduce typos. Instead, I want to embed these test cases into a pair of for loops which iterate through the positive and negative sign bit values for both the multiplicand and the multiplier. Again, all the values we get from these 2 loops will be infinite, but remember we'll have to check the sign of the infinity returned. If both operands are positive, or both operands are negative, the infinity return must be positive. For all other cases, the infinity return must be negative. I ran into a problem using loops to iterate over all the sign bit permutations. The last test case for each sign combination has the wrong sign for the multiplier. As you can see, the sign bit of the multiplier for the last case is negative, but the sign bits for all of the other multipliers in this iteration are positive. I'm sure this is due to some rookie Verilog mistake on my part. If any of you can explain what I did wrong, or better still provide working code, please leave a comment below. Thanks. Even though the sign bit for the last multiplier is wrong, the code does seem to be calculating the correct products. In the interim, I'm going to duplicate the code and fiddle with the sign bits and keep my fingers crossed that I don't screw up the whole complicated mess. Now, we finally pick up the cases where one of the operands is infinity and the other is 0. Generate all 4 sign combinations. Unlike the other products of infinity, we expect the results of these tests to be quiet NANDs. Since there are 28 test cases for multiplying by infinity, I won't include the test results here. I'll leave you to run the test cases for yourself so you can verify that all of the cases work as expected. This is our updated table of completed test cases. For the next 5 boxes in our table, where we're multiplying 0 times 0, 0 times subnormal numbers, and 0 times normal numbers, we need to test for all combinations of positive and negative multiplicands and multipliers. This is a total of 20 different test cases, and they're pretty straightforward, so I'm not going to include the test code here. To see the code for the test cases, have a look at the code from the GitHub repository. Our updated completion table is this. Now we're in a tricky place. If you remember, I implemented the code for multiplying 2 subnormal numbers as a special case which we know will always produce a 0 product. The reason this is tricky is that, in theory, the multiplication code which handles multiplying a normal number with either A normal number or a subnormal number should also correctly handle multiplying two subnormal numbers. How can I know that the special test condition I added is recognizing that we're trying to multiply two subnormal numbers and short-circuiting straight to a product of 0 rather than going through the trouble of using the more complicated data path for a full multiply? The only answer I have for this particular question is an answer I don't particularly like. I can comment out the else clause in the HPMOL module, which handles multiplication of normal numbers. When I do this, the module should always return an AND value if the test condition for multiplying two subnormal numbers fails. I don't like this solution because it involves manually changing the Verilog code, which is being tested, and it could lead to code corruption if I'm not careful. Still, since it's the first time I'm testing this code, and I'm ultimately going to fix this testability issue, and I want to ensure that all of the paths are working the way I expect, I think it's an acceptable risk to run the code this way just this one time. So, after commenting out the else clause, which handles multiplication of normal numbers, I can add the following test cases to verify that multiplying two subnormal numbers together to get 0 is being handled by the special test case which I added in part 2 of writing the multiplication module. Remember that even though the product is 0, that we still need to test all four sign combinations to ensure that the sign for our product is correct, as specified by the IEEE specification. Here are the test results for this code. If the test for multiplying two subnormal numbers was failing, the output would be quiet nands, so we know that our test for this special case is working. Now, before proceeding, remember to go back into the HPMOL module and uncomment the else clause which we commented out earlier. Since the module is under Git source code control, the safest way to do this is to run the Git command currently displayed on the screen. Our updated checklist now looks like this. Okay, we're to the part where we really have to think carefully about how we select test cases. If we were to test all of the normal times normal, subnormal times normal, and normal times subnormal cases, we would end up with billions of test cases, and as mentioned before, that just isn't practical. What kinds of things do we need to test which would be representative of the corner cases? A quick list might be: make sure that the sign bit is always calculated correctly. Test multiplication of cases which don't require the significand product to be normalized and the exponent adjusted. Test multiplication of cases which require the significand product to be normalized and the exponent adjusted. Multiply two numbers for which the product is so small that the product rounds down to 0. Do this for all three combinations: normal times normal, normal times subnormal, and subnormal times normal. Multiply two numbers for which the product is a subnormal number. Again, do this for all three combinations. Multiply two numbers for which the product is a normal number. As before, do this for all three combinations. Multiply two numbers for which the product is infinite. This is only going to be possible for the product of two normal numbers. Multiply two numbers which have significands which are minimized. That is, the significand is all zeros when the operand is a normal number, or a significand which has only one bit set to 1 when the operand is subnormal. Take these two numbers and maximize the significand but leave the exponents alone. For normal numbers, maximizing the significand means a significand which is all ones. For subnormal numbers, maximizing the significand means setting all of the significant bits in the significand to 1. These two pairs of numbers should be chosen so that their respective products are on different sides of the 0 subnormal boundary, subnormal normal boundary, and normal infinity boundary. Verify that when the multiplicand is plus or minus 1, that the product is equal to the multiplier, adjusting the sign bit as needed. Finally, verify that when the multiplier is plus or minus 1, that the product is equal to the multiplicand, adjusting the sign bit as needed. Some of these test cases will fit into more than one of these categories. If you look at the test code, you will see that it includes most or all of these cases. In my list of things to test, I included tests for minimum and maximum significance. Let's work through some specific examples to clarify what is being tested. For the 16-bit binary floating point format, the largest exponent which can be represented is 30. When we subtract the bias of 15 from 30, we have an actual exponent of plus 15. Any product which has an exponent greater than or equal to plus 16 is going to be rounded up to infinity. For a normal number, when the significand field is all zeros, the value of that number is 1 times 2 to the e power, where e is the exponent field minus the bias value. Remember, I'm ignoring the sign bit because for this particular set of tests, I'm really focused on the magnitude of the numbers being multiplied. If the significand field has all of its bits set to 1, then the value represented is the quantity 2 minus 2 to the minus 10th power times 2 to the e power. This value is derived from information found in section 3.3 of the IEEE specification. If we multiply two maximized significands from two normal numbers, their product is going to be 2 squared minus 2 to the minus 8th power plus 2 to the minus 20th power. This value is larger than 2 minus 2 to the minus 10th power, which means that we need to renormalize the product by shifting the binary point one place to the left and increasing the exponent of the product by 1. If the sum of the exponents of the two operands is already plus 15, when we renormalize, the exponent value will be plus 16, and we will have to return infinity as the product of the two normal numbers. So we pick our first pair of multiplicand and multiplier so that their two exponents add to plus 15, and both have a significand of all zeros. When we multiply these two numbers, the product still should be a normal number. We pick our second multiplicand multiplier pair to have the same exponent values as the first pair, but with significands which are set to all ones. This product must be infinite for every multiplicand multiplier pair whose exponents sum to plus 15. This test should be run for all pairs of exponents which add to plus 15, and for all combinations of positive and negative multiplicand multiplier pairs. Here is the first example. The test results confirm that the first product is a normal number and that the second product is infinite. Just as there is a boundary where changing the significand values of the multiplicand and multiplier causes the product to change from a normal number to an infinity, there are cases where changing the significand values changes the product from a subnormal number to a normal number. And finally, there are cases where changing the significand values changes the product from 0 to a subnormal number. The test code for this video includes all of these test cases. I'll leave it as an exercise to the viewer to explain why all the following test cases result in the same product. You might remember that in an earlier video I calculated the area of a circle which has a 20 centimeter radius using scientific notation. For good measure, I threw in some test cases which also compute this same value using our Verilog multiplication code. I'll leave it as an exercise to the viewer to verify that the 16-bit floating point values for 20, pi, and the area of the circle are correct. You might notice that the tests don't really spend much time testing a broad range of the possible significand values. The test cases really focus on testing various exponent values. This is deliberate and will be discussed in more detail in a subsequent video. This completes our checklist of test cases. In the next video, I'm going to revisit the Verilog code which we've written so far to see what we can do to optimize it and make it more general. Questions and comments are welcome in the comment section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.